I chose out of the stuff done in my group also to discuss a research topic that's also sitting right at that interface, showing you how concepts of condensed matter physics can affect optics and vice versa. So let's start. This is a work that basically the PhD project of two of my students, Yaron Silberberg and Yoav Lahini, and since I never reached to the end of my talks, I chose to show you their pictures right in the beginning. So this is Yaron Silberberg, Yoav Lahini, and we, as you can recognize surely, we are all standing on the shore of the Dead Sea. Let's start with the simplest condensed matter physics you can imagine. You all learned it in the first lecture of the first course of the Introduction to Condensed Matter Physics. This is the simplest concept that can let you understand the physics of lattices. And this is the model that we know as the tight binding model. And it says basically take quantum states, think about quantum wells with one state, or think about atoms with an S state, and put them in a row in a periodic lattice. And as you know, this arrangement gives you basically the Schrödinger equation for this system, tells you that each site can have an energy. The amplitude of each site is given by psi n, the amplitude at site n, where each site has its energy En and a tunneling rate which can couple each of these wave functions to its nearest neighbors. And this is written in one dimension, and actually everything I will tell you about today is happening in one dimension. So this is condensed matter physics. This is basically today, it's 80 years old. It was written first. It's very hard to get the exact reference. But I believe that the first one to write this equation is actually Felix Bloch. And of course, he's written it in 1 and 2 and 3 dimensions to explain the properties of metal, because this is the simplest equation that will let you understand band structures, ballistic motions, all the good properties of condensed matter that were hard to understand without quantum mechanics. Now, we in optics can simulate exactly the same system. In our world of optics, instead of thinking about quantum wells, we think about waveguides. And if you want to discuss a single state, let's talk about waveguides that support a single mode. And all we need to do in order to reproduce the system is to put many of these waveguides side by side so that they are coupled to each other. The distances are such that light that propagates in one of these waveguides can couple to the next nearest neighbor. And when you analyze the system, it is described by exactly the same equation as the tight binding equation. So what this tells you is that the amplitude of the wave in waveguide number n is, of course, the phase is changing according to the propagation constant or the index of refraction of that waveguide, but the light can also couple to the nearest neighbors coupling coefficients. And of course, you can make these waveguides, the way we make them actually is by lithography in gallium arsenide systems, but really we don't need to understand the details. But I promise you that we have excellent control on how we make these, so we can really control both the beta ends, the indices of refraction of these waveguides, and the coupling coefficients, which are determined by the distances in which these waveguides are put together. So we can make these systems periodic to simulate exact periodicity, or we can make them aperiodic to study various problems, and that's something we have been doing and many other groups in the world have been doing in the last 10 years. The group of Moti Segev, who sits here, has been one of the leading in pushing this to higher dimensions than one dimension. My group has worked mostly on one-dimensional structures. One additional advantage of the optical system is that we can shine high intensities into these systems, and then suddenly things become nonlinear. The index of refraction is now dependent on the amplitude, and therefore you start to see effects that relate to interactions between photons. Or if you want, you study this system not only at a single electron limit, but also for interacting systems. So you can experimentally study this simple model even with interactions. But today I will not discuss interactions at all. Everything today will be linear and simple. So why this system in optics is interesting? Because we have excellent control on everything. I didn't point it out, so maybe I should. The system in optics, of course, is slightly different. In quantum mechanics, you think about time, the evolution of the system in time, while in optics, it also evolves in time, but as it evolves in time, it also evolves in space. The wave that you launch at z equals 0 is propagating as time passes by along z. So we like to write the equation in z rather than in t, but beside that, the two equations are just the same. But because we move to space rather than time, things become experimentally much simpler. If I wanted to do the experiments that I'll describe to you in electronics, I'll have to put electrons on particular sites and watch them disperse. But in optics, all you need to do is to shine light on one of the waveguides and see how it diffracts. And that's much easier to do and very practical. And that's basically what it tells you, that you can really very precisely tailor the initial conditions of these experiments by shining the light right where you want it and see how it evolves. You can directly measure the evolving wave function, and the big advantage, you can actually look at the wave functions and take a picture of the wave function. That's something that in electronics you would love to do, but it's very hard. You have excellent control of the potentials. You don't have to make a periodic array. You can make aperiodic arrays with excellent control of all parameters in the system. And in principle, you can measure what would be in quantum mechanics time-dependent potential, basically vary these waveguide structures as you propagate in them. So you have a very nice system to work experimentally, and indeed, we and many other groups have pushed this analogy very far. Basically, almost every effect that has been predicted in quantum mechanics coming out of these periodic potentials has been actually already demonstrated in optics. Things like Bloch modes and Bloch oscillations, Zener tunneling, Anderson localization, quasi-crystals. These are, of course, two-dimensional things that Moti Segev's group has demonstrated. And this has been done now for 12 years. It's been reviewed several times. It's really has been a very productive area of research. Let me take you again to the very basic principles of this, because I want to take you now to the next stage in which we are going to push the system. So again, I want to remind you, this is the perfectly periodic tight-binding equation. I will remind you that from this equation, when you actually solve for the normal modes of the system, you find that they are all arranged in a band of energies. Again, the band is inverted to what you are used to, because in optics, there is the sign inversion, so the ground state is actually here, and the excited states are here. The ground state is this state where all the sites are in phase. The highest energy state is the state in which every other state is out of phase, and all the other states are in between. So this is the normal way that you are used to look at the system in electronics. You immediately take this equation and go to the K-vector Fourier domain to analyze the normal modes. But in optics, it's much easier for us to think about space, because what we are going to do, we are going to launch light in one site or in several sites. So let me tell you something that usually you don't hear about in electronics. What happens when you really put an electron on one site and watch it evolve? And what this equation will tell you is that the evolution of if you put an electron at initial time t equals 0 on one site, site number 0, and watch it evolve, it will evolve in time, or light will evolve in space in this manner. Actually, it will get broader and broader with time, but not in a uniform way. Actually, most of the probability to find the electron will be in two lobes, which are called the ballistic lobes, that are propagate away from where you put the electron with a constant velocity. So this is very well understood. This is basically when you put an electron on one site, of course, you excited all the modes of the system with equal amplitudes. And this is what coming out of the summation of all these modes with the revolving phases. And this is something we can actually watch and see. If you just take a waveguide sample like this and cut it at a certain distance and take a picture of what comes out, you'll see something like that. You see, we started with light at site equals 0. After a certain distance, you see the pattern becomes elongated. Two lobes, which contain most of the energy. This picture, actually, this photo is not very linear with the intensity. It's distorted a bit, but most of the probability or most of the amplitude is in these two lobes, and the center has this oscillating pattern that you can see down here. So this is the impulse response of your system, if you want. I want to point out that this system is much richer than just the tight binding approximation. You can take this system, as you know, it's a periodic system, periodic optical systems. things are not ending with one band, there are many bands. And this is an old picture that shows you that you can actually take a real photo of the Floquet-Bloch modes that belong to each of these bands. We have done it, and this is all stuff. But again, let's think about now the first band, the tight binding model. And what I want to do now is to ask the question of photon, of single photon, or if you want single electrons. Everything that I told you about up to now has been wave theory. It's the wave theory of periodic media, very well understood. We have good intuition to it. Now, I want to ask what happens when I put real quantum particles, photons or electrons, into these systems. Now, these things have, now really you start to put quantum mechanics in, not just waves. And we want to ask what new features will come out of the fact that these things are really quantum particles, they have quantum correlations. Let's ask the first questions that come to mind when you think about these things. Now I'm going to put a particle in there. What will happen? I have to do the formalism the right quantum mechanical way. I have to write now the Heisenberg operators for creation and annihilation of photons in these waveguides, or electrons if you want, and propagate them. And I will not discuss the theory much, but of course when you send a photon in such a structure, or a single electron in such a structure, what you reproduce is exactly the wave theory that we have analyzed so far. Basically, what the wave that we found is just the probability to find a photon or an electron in particular sites. So there is nothing new when you come to ask questions about photons. All you have to say is to interpret the wave as the probability to find the wave intensity is the probability to find a photon in a particular site. So far, nothing is different. We know that quantum features will come about only when we start to think about correlations. And to discuss correlation, we have to start to think about putting not just one photon or one electron, but we are going to put a few of them. And we'll start today by just putting two. So we are going to ask questions, what happens when we put two photons in these structures? So now we have a freedom. We can put them into separate waveguides. We can put them one on top of the other. We can put them like this. And we should ask questions about correlations. We put two photons, one here and one there. What is the probability to find one in waveguide number P and one in waveguide number R after propagation of a certain time or a certain length? This is the type of questions we are going to ask. Why we expect things to be interesting? Because there is this famous phenomena called the Hanbury-Brown twist, or two-photon interference, or two-particle interference. If these two particles are not distinguishable, really there are two events. When we put two photons, say, in two inputs, we measure them in two outputs, we don't know. We have no way to know whether this happened or that happened, whether this guy went here and this guy went there, or the other way around. These two events are in principle indistinguishable, and therefore we have to interfere them. And this quantum interference is going to lead to a lot of interesting effects. Some of them are surprising, as I'll show you right now. Okay, so I'm going to show you some simulations. They are very simple simulations. First of all, let's just put two photons in a single waveguide. Now, if I put two photons in a single waveguide, then these two things are the same. And if these two things are the same, so they come from a single waveguide, there is no difference between two things. Nothing interferes. And therefore, when we put two photons in the same waveguide, really what we should get is just the same single photon picture twice. And this is the type of results I'll show you, so I want you to understand what it means. It means I have two detectors, one in location Q and one in location R, and I'm showing you what is the probability to get one click at R and one click at Q. So this point here tells you that I detected one photon, one click in waveguide number, I can see from here, -8, and one of Q at -8. And this gives you a matrix of correlations. And what you see here is the correlation. When you put the two photons one on top of the other, what you get is really a product of two patterns. The two patterns are just the patterns that we have seen before for a single photon. So the two guys have propagated sort of independently to each of the two outputs. And what you see is a product state of the two independent propagations. So this is sort of trivial and not interesting yet. But now let's put the two photons into waveguides next to each other. So now the two patterns are not the same. The one going to the left, one going to the right is not the same as when they cross on the road. And the matrix now looks very different. So let's think what it means. Compare it to this one. We see these two lobes. These two lobes tells you that if one photon arrived to waveguide -8, which says on that side, then the other photon also went to waveguide -8. So they went both to the left or both to the right. You never find them here. This peak here or this peak there is that when one goes to the left and one goes to the right. They never do that. They decide together, let's go to the left or let's go to the right. This is something in quantum optics called photon bunching. It's not unexpected. I want you to remember each of them by itself is doing its regular thing. If you just measured one photon distribution, you'll see the regular one photon distribution that I predicted with wave theory. It's only when you consider correlations that you see this funny anti-bunching. So if I integrate this table along this axis or along that axis, I'll get exactly the same as this table. So it's only when the correlations are considered you see these strange phenomena. What I do now, I put the two photons with one waveguide apart. So there is one waveguide in between and two waveguides. So I put what I call -1 and 1. Now they can reach all four lobes. But you see, again, this is very different than this. What you see now is that they kind of decide together. Either we all go to the lobes, to the sides, or we all stay in the middle. But you never find one goes to the lobe and one stays in the center region. So they have sort of decide, or they have the quantum correlations that force them to go together to certain regions. Now, since all this is theory, I can easily change my calculation to think about fermions. And fermions means that either two electrons with the same spin or quantum particles of other sorts that behave like fermions. And when I put them next to each other, the bosons did this bunching, only going to these two corners. It's not surprising that the fermions do anti-bunching. They decide we never end up in the same lobe. We go to opposite lobes. So when I put them one waveguide apart, you remember the bosons went to all four corners. The fermions do this funny thing. They say, one of us goes to the corner, and then the other one has to be distributed in between. Never go to the other corner. You never find them in the same corner, on opposite corners. You find one in the corner and one spread in between, so you draw this funny frame around the center. All this coming from these quantum correlations of the two particles. Now we have freedom to think about more complex way to put particles. For example, we can put an entangled pair of photons. We are going to put the photons either here or there, either the two of them here or the two of them there. This is an entangled pair that we are launching into this arrangement. And interestingly, this entangled pair behave as if it was fermions. And if I put them with one waveguide apart, I can really reproduce the same frame that I showed you before that I could generate with fermions. So somehow you can, even though I cannot do experiments with fermions in one waveguide lattices, we can definitely do experiments with entangled photons and reproduce the same patterns that we predicted with fermions. Everything up to now was in ordered lattices, and I want to show you what happens when we put disorder. As I told you, we have excellent control on these patterns, so we can produce patterns with any disorder that we want. Now, you all know what disorder will do. If ballistic motion will do this is the ballistic expansion of a wave function. When you have disorder, everything, of course, is randomized. But when you average over many realization of randomness, what you get, of course, is localization. This is classical Anderson localization. The wave function is localized in one region of space. And after enough time, things are completely localized. But I want to show you results from this region here where things are not completely localized yet. The reason I choose this region because I still want to have a little bit of ballistic thing to relate to. So I'm going to show you the same sort of correlation matrices as we did before, but now averaged on many realization of randomness. So this is what happens when I put two bosons in two sites next to each other. You remember before I got bunching. Now I get also localization. So sometimes they bunch together. Sometimes they localize. Sometimes one is localized and one is going ballistically. So this is this lobe. They still, even though you randomize the phases, by this disorder, you still never find them in opposite sides. This is for bosons. This is what fermions do. There is the anti-bunching, again, sometimes localization, but I want you to zoom in on the localized part to see a very funny phenomenon. What you see here is that the fermions have localized with an interesting order of what we call checker marks, checker pattern here, which predicts that the two fermions, if I draw the distance that I expect to find these fermions, you find that the fermions are not just localized, but they tend to be localized either separated by one site, or by 3 sites, or by 5 sites, but not by 2 or 4. Very surprising. Nobody has imagined this or predicted that. If I do the same calculation now with different input, now the bosons do this funny thing. The fermions don't. The fermions do something very surprising. The fermions decide that they really hate to localize together. You find that one is localized, so one is near the center, and the other went ballistically. So you see most of the amplitudes in these 4 corners here, 4 lobes here, very little here. So now the fermions are hardly localizing. The bosons have this oscillating correlation function that predicts that the bosons will be either on the same site or separated by 2 sites or 4 sites, but never by 1 or 3. We understand why this happens. I have no time to go into the details, but this really is a very interesting story. Now, of course, I have to tell you something about experiments. Now, these experiments, we really want to do them with single photons. I cannot show you results with single photons yet. But Hanbury, Brown, and Twiss, that these interferences are named after, never did experiments with photons, or not with single photons. They did experiments with classical light. And this is because this interference that I talked about also happens with classical light, only that if I told you before that it's either this or that, with classical light, there could be other options as well. The result is that the classical intensity correlations that Hanbury, Brown, and Twiss discussed will have less contrast than the quantum effects, but still you can see the behavior. So I want to show you the results of 2 experiments with classical light. The way you do it, you shine classical incoherent light in these 2 inputs. You basically, really the way we do it, you send coherent light, but you randomize the phase. You look at the output with each random realization of the phase, and then you find the correlation matrix, and you see the bunching very clearly, but you see the contrast is not as high as I predicted in the quantum mechanics. So this is the bunching experiment. This is what we predict quantum mechanically. This is what we see classically. The other experiment is when we shine light into waveguides separated by one waveguide. This is what we predicted. This is what we measured. You see there's a lot of similarity. So you see a lot of this stuff with classical light, but a lot of the more interesting patterns, the checker patterns that I predicted, we still are working on because these are really tough quantum experiments to do with these waveguides. So this opens a lot of interesting questions. Some of them are listed here. I will not read them. The conclusion from this talk is the following, or the bigger message. Optics gained a lot of insight from condensed matter physics. A lot of the concepts I talked to you about really are borrowed from condensed matter physics. But when you do things in optics, sometimes you are brought to ask questions that were never really asked in condensed matter physics, mainly because things are not doable practically. You cannot really put electrons one next to each other and see what happens. We can easily do that in optics. So that opens a lot of interesting questions in very basic quantum physics that we are hopefully will address in the coming years. Thank you very much for your attention.